In section 12.2, we want to look at injective and surjective functions. So we're going to start by just drawing out some functions. And because these functions are from finite sets, and especially small finite sets to other small finite sets, I'm going to draw them in my favorite way to represent functions, which is what I call potato diagrams. So we draw a potato and then another potato. This first potato is going to represent my set A. So since A just has 1 and 2 in it, I can draw those in my set. The second set is going to be B. So that'll be 3, 4, and 5. So we'll put those in the set. And now I'm going to represent this function by drawing arrows. So I could say that that 1 in A can get mapped to 3, and maybe 2 goes to 4. Right, so that's going to be this function. I could also represent the same function using a table. So I would just say 1 and 2 are my elements in A. So if I call those maybe little a's, then f of little a, the function mapping of little a, 1 gets mapped to 3 and 2 gets mapped to 4. Or if we were going to represent this in sort of set world, we would say that this function f is the set 1, 3, 2, 4. So those are sort of all different ways you can think about representing this function. Okay, but I'm going to focus on these potato diagrams. So that's my first function f. Let me draw another one that also goes from 1, 2 to 3, 4, 5. I could have 1 mapped to 3, and then I can have 2 also mapped to 3. Right? It's okay that they all both end up at the same spot. It's kind of hard to see where it's actually mapping to, so maybe I should make it go a little bit further over, really make it clear that it's going all the way to 3. So 1 and 2 both can map to that same spot. That's okay. And they could have both gone to 4, they could have both gone to 5, they could have gone to 4, 1 could have gone to 4, 2 could have gone to 3, right? So we could have all sorts of different functions here. So we could have had, maybe that was my 4, and then 3 is up here, right? Those arrows can cross each other, that's fine. And then I still have my 5 down there. Okay, now over on the other side, I'm going to do the same thing, but I'm going to think about functions now that go from B, so that's my bigger set, 3, 4, 5, to A, 1 and 2. So 3 can go to 1, 4 maybe also goes to 1, and 5 goes to 2. Or maybe we have 3 goes to 1, 4 goes to 1, and 5 goes to 1. Okay, so let me draw a couple things that aren't functions so we can see what those look like as well. So what's going to make it not be a function? Let's say I'm going from B to A. I could say that 3 goes to 1, 4 goes to 2, and then just have 5 go nowhere. Right? This is not a function because f of 5, or maybe g of 5, is undefined. We didn't say what it should be. And then I could also do something like this, where we have 3, 4, 5, and 1, 2. If I send 3 to both 1 and 2, and then maybe 5 gets sent down to 2 and 4 gets sent to 1, this is not a function. Since we have g of 3 equal to both 1 and we also sent 3 to 2. Right, so you have to send it somewhere. You can't send it to 2 different places. So those are not functions. Okay, so let's look at the things that we have that are functions and see what we can find about them. Right here, 1 and got mapped to 3, 2 got mapped to 4, but nobody got mapped to 5. So one thing I could say about this is that 5 is not in the image, or what some people call the range of f. I don't hit everything in my codomain. Right, so that's the difference between a range and a codomain, if you've heard those different words before. The range is actually the stuff that you hit. So my range here is just going to be 3 and 4. And my codomain is the stuff, the target set where I was headed. So the codomain was the whole set B, 3, 4, 5. Down here, my range is just equal to 3. So that's also not the entire set. And down here, my range, the stuff that I actually hit, is 3 and 4. So none of these actually hit the entire set. They all left somebody off. So what we would say is that these functions over here are not, there's two different words we're going to use. The first one is surjective. That's the one maybe you haven't seen as more common. Or we could say that they're not onto. Since the range is not equal to the codomain. And we'll see a more formal definition of that in a second. Now, what else do we notice? Some of these functions here send two different elements to the same element. So that function did it, this function did it, and this function actually sent 3 to the same element. So we have multiple elements getting mapped to the same element. That means that we're not one-to-one. Or another word for one-to-one is injective. So these functions are not injective because they're both not one-to-one. There's two different elements get output to the same element. So that's the main thing that we want to work on in this section, is defining these words injective and surjective, which you might have seen before as one-to-one and onto. Okay, so I have the definitions from the book here for our injective, surjective, and bijective, my green terms here. So a function f from a to b is injective, so that's the one that means one-to-one, if for every elements a and a prime in our set A, if those elements are not equal to each other, the inputs aren't equal, then the outputs aren't equal. All right, so I can't have two unequal elements getting mapped to the same element. And it's surjective, or onto, if for every element in that codomain B, there's some element in the domain that gets mapped to it. So for every B in B, I can find an A such that f of A equals B. And then it's bijective if it's both surjective and injective. So bijective is just the one-to-one and onto. Okay, so just let's think a little bit about how to actually prove these. For injective, we have that for all A and A prime, A not equal to A prime implies f of A not equal to f of A prime. So because if I have this implication here as part of my statement, that's what I need to prove. I should assume A is not equal to A prime, and then show that f of A is not equal to f of A prime. But often we're going to want to do the contrapositive. So we'll assume we have A and A prime in A, and that f of A equals f of A prime. And we'll show that the only way that the outputs could be equal is if the inputs were equal to begin with. Right, because that's how I would show the contrapositive of this statement. So that's what we're going to often do for that injective proof. For the surjective proof, we're going to need to show that for every B and B, there is some A and A with f of B equal B. Right? So we take some fixed but arbitrary B and B, and then we prove why there must be that A. So that's how we're going to go about doing those surjective proofs. So we'll see some examples of those on the next slides. Okay, so let's look at this example here. We have this function f, which is going from r minus 0 to r, and it's defined by f of x is equal to 1 over x plus 1. And I want to know if it's injective, if it's surjective, and then if it's not one of those, can we change the domain or codomain to make it bijective? So let's start with the injective, surjective, and then we'll talk a little bit about that thing at the end, the changing the domain and codomain. Okay, so for injective, I want to see if there's two different elements that get mapped to the same element. So I can really think about the graph of this function a little bit to kind of give me some intuition about whether or not it should be injective or surjective. So I know 1 over x is the asymptotes at 0, and then I'm going up by 1, so I'm going to have a horizontal asymptote at 1. So it's going to look something like, let's see, this and this. When I'm checking for injectivity, that's when I'm going to use my horizontal line test to see if there's any y values that get mapped to by two distinct x values. And we should be able to see by that horizontal line test that's not going to be true. So that's not a proof. It kind of gives us our intuition about whether or not we should try to prove this or disprove it. So now we can actually try to prove that. So I'm going to use that contrapositive approach. So I'm going to assume that some x and some y are in my domain r minus 0. And I'm going to assume that the outputs are the same. So f of x is equal to f of y. Or that means that 1 over x plus 1 is equal to 1 over y plus 1. I know that x and y aren't 0, so those quantities are going to be well defined. So I'm good. And now I just want to try to show, using algebra, that x has to equal y. So I can subtract 1 from both sides. One over x equals 1 over y, and then I can cross multiply to get that x equals y, which is what we wanted to show. Thus, we can conclude that f is injective. Anytime you have two values giving the same output, they must have just been the same input to begin with. Okay, so now let's check to see if it's surjective. So for surjective, I want to check to see if every single y value gets mapped to by at least one x value. So again, it's kind of like doing that horizontal line test, and I'm checking to make sure every single horizontal line hits something. So if I have a horizontal line that never gets mapped to, that means that value is not going to be in my image or my range, which means I'm not surjective. So we can sort of see from this that we get that it looks like we're never going to hit 1. That's where my asymptote is. So I can say it's probably not going to be surjective. So let's say the function f is not surjective. And to show it's not surjective, I can just say what it doesn't hit, right? Since f of x is never equal to 1. Now I actually have to show why it's never equal to 1. So we could make a counterexample maybe. So we can kind of prove by contradiction that. So if it was, then 1 over x plus 1 would have to equal 1, in which case 1 over x would have to be 0, which is never true. I guess we could even then multiply by x, which gives 1 equals 0, which is impossible. So I'm writing statements that aren't true here, but I'm making sure to always have some sort of words along with them, so I'm never asserting them as true. right? I said if it was true, that's a if there, then this must be true, in which case this must be true, which would give us this, and I know that's not true. So because I have all those words, I can sort of fix it. Now, okay, the last part of this is kind of strange, but what it asked us to do was to adapt the problem slightly, changing the domain and codomain to make it bijective. Right, so I already had injective. The one I didn't have was surjective. And surjectivity is sort of easy to hit or to fix, right? So surjectivity just means you're going to hit every value in your codomain, but you can always restrict your codomain, make it smaller and smaller, so you know that you are actually hitting everything in it. So I know, based on the picture we have so far, that the image of f, so the stuff that we're actually hitting, which is the same as the range of f, looks like I'm hitting everything except for 1. So if I change this to be the codomain, then we're going to be surjective, because then the image equals the codomain. So we can always make a function surjective by just changing what that codomain is, which is why it's very important to write the codomain before we ask this question. So let's go ahead and we'll pop it into another slide. We'll change that codomain, and then we'll show that new function is surjective. So to show this function is surjective, I want to show that every element in my codomain gets mapped to by some element in my domain. Again, we have the same function that we were looking at in the last problem. So we're going to start off by letting some, we'll call it a y, be in that codomain. And I just need to find some x that gets mapped to that y. So what I like to do is sort of do that as my background work, right? So I want to try to find which x that gets mapped to this. So then if I just solve for what x should be, I get 1 over x equals y minus 1. So I can swap my denominators. 1 over y minus 1 should equal x. So then I can say let x equal 1 over y minus 1. Since y is not equal to 1, this is well defined. I can actually divide by y minus 1. That's not going to cause me a problem. Then f of 1 over y minus 1 is equal to 1 over y minus 1 plus 1, which is equal to y minus 1 plus 1, which is equal to y, which is what we wanted to show. So we found some x in the domain, right? I guess we should let's include that. Note, x is not equal to 0. That's all I needed to do, because I needed to make sure it was actually in my domain. It's well-defined. It's non-zero, so it's in my domain, and f of it equals y, so we're good to go. So that's how we can actually show this is surjective. So here's a question for you to think about a little bit. You want to show that g, the function g, going from z cross z to z cross z, defined by g of m and n is equal to m plus 2n is bijective. So think about that a little bit. Think about how you would show that. You're welcome to read about it in the book, and we'll discuss that together in class. All right, so if we look back at some of our nice example functions we had right at the beginning, we can see that none of our functions from a to b were going to be surjective. Right? We always had those leftover elements over here, and none of the ones over here from b to a were going to be injective. And we can think a little bit about why that's true. Right here, I have 2 elements in A starting off, and then there was 3 spots in B. So there's no way that those 2 elements could hit all of those 3 spots. And when I went back the other way, I had 3 elements getting mapped into 2 of them, and there was no way that those 3 elements could go to 2 spots without them overlapping. So this idea is related to what's called the Pigeonhole Principle. So we'll see a little bit about what the Pigeonhole Principle says on the next slide, and how it's related to these sets being injective and surjective and based on the size of the sets. And then we'll see one example of using that Pigeonhole Principle. Okay, so what does the Pigeonhole Principle say? The Pigeonhole Principle says if you have a whole bunch of pigeons and a whole bunch of holes that they're going to fly into, if you have more pigeons than you do pigeonholes, then 2 of those pigeons are going to have to end up in the same hole. And if you have more pigeonholes than you have pigeons, then one of those pigeons is going to, or one of those holes is going to end up empty. Right, so if we think about this makes sense. If there's more pigeons than holes, they all have to end up in a hole. They can't end up in different holes because there's not enough, so 2 have to end up in the same hole. If there's more holes, then the pigeons can't fill them all. There's just not enough pigeons to fill all the holes, so one of those pigeons will be empty. And we can definitely think about this in terms of functions. So there's going to be this function version of the Pigeonhole Principle. So if you have functions between finite sets, a and b, and you're taking that function right from a to b, if there's more stuff in a than there is in b, then 2 things from a must end up in the same hole, which means it can't be injective. And if there's less stuff in a than there is in b, then you can't cover all of the stuff in b, so you can't be surjective. So we can use injectivity and surjectivity to sort of know some stuff about the size of these sets. And we'll actually see that this is helpful. We're going to actually use this idea later when we're talking about infinite sets to be able to think about different sizes of infinite sets by thinking about whether or not there's injective and surjective functions between those sets. Okay, so this is a surprising application of the Pigeonhole Principle. So as you're thinking about this question, definitely think about it in terms of the Pigeonhole Principle. So let's say I have a set that has 10 integers between 1 and 100. Then I can pick off 2 different subsets, x and y, so that the sum of the elements in x equals the sum of the elements in y. Right? So no matter which 10 numbers I write down, as long as they're between 1 and 100, then I can always pick off some subset of those, and I should be able to get the sum of those subsets to be equal. So let's try it. So I've got 10 numbers written down here. I'm going to pick a subset. So let's say I pick these ones. 60, 75 is what they add up to. And I was really lucky, / planned it well, where I can also find another set that also gives me 75. Now, had I not picked my numbers as well, right, maybe if I had originally picked 90 and 89 in my subset, then I can't always find another set that equals those. But I can always find 2 sets that when I add those together, they're equal. So think about how you could prove that, and we'll talk about that in class.